And now we can take a look at this. All right, so this is example 7.7. We're going to finish up chapter 7 today. So in example 7.7, we have this car that's turning on a banked track. Notice we have this track that's banked at this angle of theta. And notice how they do the force diagram on the car. We have the force due to gravity that's acting on this center point on the car straight downward. It's not perpendicular to the track because the track is not flat. So it is straight downward to the earth even though the track is not level with the earth. And then you have a normal force that the track exerts on the car, and notice that the normal force is perpendicular to the track because it's supposed to be. All normal forces are contact forces, and all contact forces are perpendicular to the surface that is causing the contact force. And then they actually draw a free body diagram over here. So there's no car in this free body diagram. And they still show mg, or the weight of the car, straight down, so they call it negative mg. And then they split this normal force, which is pointing upward and to the left. They split it into an upward force, n cosine of theta, and to a leftward force, which is n sine theta. So they essentially just split it into components here, which is perfectly fine. Now, another alternative way of doing this might be to put your axis on the track here, your x-axis on the track, and your y-axis perpendicular to the track, but then you would have to break the weight force into two components, a y component and an x component. It just kind of depends on how you split up your, or how you choose your axes. But they choose their axis to be horizontal and vertical for x and y. And then they're going to go ahead and find the centripetal acceleration. How do you calculate the centripetal acceleration? Well, what you got to do is you got to essentially add up all the forces that are in this picture, essentially, that are pointing inward, because all the forces that are pointing inward are going to be the centripetal forces, and that's this force right here, n sine theta. So what we need to know is we need to know that normal force. We have to figure out what that normal force is to find that centripetal force. And what we want to do here is we want to add up all of the forces that are in whatever direction. So the sum of all the forces have to equal the mass times the acceleration. And then you do that in two dimensions. So in all dimensions, in every dimension, you have just mass times acceleration equals the sum of the forces. And the only forces involved are the normal force and mass times gravity. But then we do just the y component. And in the y direction, so let's go back to our picture up here. In the y direction, which is the up and down direction, this car is not going anywhere, which means its acceleration in the y direction is 0. And so if its acceleration in the y direction is 0, then mass times acceleration, which is on the right side of the equation now, is 0. And everything that's in the y direction is just n cosine theta, which is that component of the normal force, which was upward, and the weight, which is downward, negative mg. And so you just add n cosine theta and negative mg together, and that has to equal 0. The great thing about that is what that gives us is it gives us a formula for the normal force. It's mass times gravity over the cosine of theta. Now, in this particular problem, theta is 31 degrees, so we know everything that we need to know in that problem. We know the mass of the car, we know the gravitational force, we know theta, we can calculate the normal force. But then we want to know the centripetal force, right? Well, the centripetal force is not n cosine theta. It's not this one. It's n sine theta. It's this one over here, because that's the one that points inward on the turn of the track. So force centripetal, which is F sub c here, equals n times sine theta. And since we know that n is equal to mg over cosine theta, we just replace n with mg over cosine theta. And then you multiply it by sine theta, and you get mg sine theta over cosine theta, which is mg times tangent of theta. Well, again, we still know everything in that equation. So we can plug in numbers for that. But what they're actually asking us for is the centripetal acceleration. So we need to divide by the mass of the car, and we do that. We get the centripetal acceleration, and it ends up being g times the tangent of theta. We just multiply g, tangent of 31 degrees. You get 5.89 meters per second squared as the centripetal acceleration as the car goes around that track. And then we want to find the speed of the car. Well, the speed of the car, if it's going around this circle that has a radius r, has a centripetal acceleration a sub c, which we already know, 5.89 meters per second squared, is going to be solved by this equation, A equals v squared over r, for centripetal acceleration. So then we just solve for v, taking the square root of both sides after we've solved for v, and we get square root of 316 meters, which is the radius of the track, times the centripetal acceleration, which is 5.89 meters per second squared. And you're good to go. I think the hard thing for some people is to recognize that the centripetal force is that force. It's the part of the normal force that points inward. So if you're turning left, if you're turning around a track in a leftward direction, which this car is, then that centripetal force is going to be the sum of all the forces that are pointing to the left. Right? The sum of all the forces pointing to the left is your centripetal force. And then you divide that by mass and you get acceleration. This one tends to confuse students quite a bit. And quite honestly, it confuses a lot of people, not just students, because of the math gets a little bit tricky because of different signs of things. But what you got to think of is what is it that makes you feel weight, right? There are two things that make you feel weight. Either a gravitational field is pulling on you and you're standing on something that's not allowing you to accelerate, so it's stopping you and you're pressing against that thing like the earth or a floor or whatever. And that pressing against the floor as gravity tries to accelerate you is what you feel when you're feeling weight. But the other thing that can make you feel weight is if something underneath your feet or underneath your body or whatever accelerates upward towards you. Like an elevator, for example. When you're in an elevator and you are on the bottom floor and you go upward, when it accelerates upward into your feet, you actually feel a little bit heavier than you normally would, right? And so that's like adding weight to you. It's like adding more acceleration to G, in other words. So a good way of thinking about this is let's go to Educreations really quick and see if we can make some sense of this. I've got an Educreations window open somewhere, I thought. Maybe not. Okay, let's go back here. Bless you. Oh, come on. How do I start one of these things? There we go. Dashboard. Physical science. Physics summer. Lesson. Create a new lesson. There we go. Okay. There we go. Okay, so, wow, this page needs to be bigger. But anyway, that's okay. It's kind of hard to do Educreations on a mouse pad, so bear with me here. But let's imagine that we're in an elevator. So here's our elevator. And we already feel stick figure. Woohoo! Man, I got that nice feedback. Anyway, we already feel our weight because of the acceleration of gravity, this negative g acceleration that we feel downward. And what that negative g acceleration does, it accelerates our body until we hit something. And in this case, it accelerates our body until we hit the floor of the elevator, and we feel that weight. But what if the elevator itself is accelerating upward with an acceleration of a, right? Positive a, for example. So it's going upward. What ends up happening is that we feel this combined gravity, you could think of it as, of A plus G, but since that gravitational thing that feeling is downward, we put a negative sign on it. Now mathematically you can figure this out. Mathematically you can work it out, but I think it has a tendency to confuse people more than anything. We'll see it worked out in the example. We'll take a look at that. But essentially our combined gravitational feeling at that point is the sum of gravity and whatever acceleration you're feeling in the opposite direction of gravity, or whatever acceleration that your body is being accelerated with. and then you throw a negative sign on the front, right? It's kind of like combining the accelerations, but even though they're going in different directions. And the different directions is the thing that really confuses people most of the time, right? So anyway, just needed to point that out really quick. Now let's go back to the example. And in the example, it's not an elevator we're dealing with. It's actually a roller coaster. But it's the same concept. In the roller coaster, we have, we're coming up this hill here, and we go over this loop and down through this loop. And any of you have been on a roller coaster before, you know very well that at the top of the roller coaster, you feel much lighter, even though you still feel your body pushing into the bottom of the car, but it doesn't feel anywhere like when you're at the bottom of the loop. Because when you're coming to the bottom of that loop, it's just like somebody is breaking your shins or something. There's so much gravity you feel down here. And so we want to figure out what it is that we feel. Well, what are the forces that we're going to feel at the top and at the bottom? Well, at the top of the motion, we're going to feel our mass times gravity pulling us down. Gravity's going to be pulling us down, right? And there's a centripetal force that's actually pulling us downward as well, right? So there's not a whole lot of force that's causing our weight. At the bottom, we have our weight pushing us down and centripetal force pushing us up, right? And those two things are in opposite directions, and that's more like the elevator. So force is pushing in opposite directions. Centripetal force is pushing us upward. Gravitational force is pushing us downward. In this particular problem, they want us to know what speed must the car have so it will just make it over the top without any assistance from the track. And what speed will the car subsequently have at the bottom of the loop? And what will the normal force be on the passenger at the bottom of the loop if the loop has a radius of 10 meters? And it turns out that the radius of the loop does make a difference, right? So let's take a look. The speed at the top of the loop, how are we going to figure that out? Well, first of all, we're going to write Newton's second law. We've got forces at the top and at the bottom. And at the top of the loop, we have a normal force with the track, and we have a gravitational force on the car. So there's a normal force with the car and the track and a gravitational force on the car trying to pull it away from the track. And those have to add together to be equal to mass times the centripetal acceleration, since the car is only feeling an acceleration in one direction, towards the center of the loop, because the track is not doing any assisting. It's the only acceleration that you're going to have for the car overall. We're going to set n equal to 0 at the top of the loop, because we're going to say that at the top of the loop, the car is not, I guess they're going to say that the car is actually not going to be pressing up against the track. And I suppose that's a fairly good assumption to make. Most of these all these tracks that have loops in them have a double track on them, so that when they're on the top, it actually switches to a different track to keep it from falling off. So it's almost like the car has gone weightless. So I guess that's okay. And we have this force of gravity that acts towards the center and provides the centripetal acceleration. So essentially, when you solve this equation in that case where n is equal to 0, then you get the gravitational weight is equal to the centripetal force over here. So centripetal force being centripetal acceleration, v squared over r times mass, and then of course just the regular weight on the other side. When you solve that for velocity at the top of the track, you get the square root of g over r. And it's kind of interesting. It doesn't depend on the mass of the car. It doesn't depend on anything except the gravitational constant g and the radius of the radius of the loop, turns out. Now, are any of you interested in roller coasters? Is it an interest for anybody? Because if it does, you like to ride them? Well, you know, there is an entire field in mechanical engineering where these engineers, all they do is design these roller coasters and build them. It's kind of an exclusive club. There's not a lot of them, and you have to be good at them. And essentially what you have to be a roller coaster engineer, essentially, is you have to be a huge lover of roller coasters, and you have to be a little bit crazy. But this is the kind of stuff that they do because roller coasters are generally not powered by anything but gravity. They lift you up to the top of the roller coaster and they just let you go. The best roller coasters in the world are made that way with nothing to power them. There are some roller coasters that do have power to them, but not many. Most of them are just gravitationally powered. So they have to know things like this. They have to know what the velocity of the cars is going to be at the top so they can know how to build, how to build the cars to withstand those kinds of velocities and the accelerations. They have to know everything else. They have to know how high to build the track so that they can get it going. So all these things are very, very much physics things. In part B, they want us to find the speed at the bottom of the loop. Well, this is going to be a conservation of energy thing. The car at the top of the loop is at a particular height according to the radius of the loop, and it's going to be the height is going to be twice the radius. And so it's just going to be conservation of energy. You're going to have a potential energy at the top, and you're going to have a kinetic energy at the top, right? Or a kinetic energy at the bottom, rather. And actually, you're going to have a kinetic energy at the top, you're going to have a potential energy at the top, and you're going to have a kinetic energy at the bottom, and a potential energy at the bottom. But anyway, they just calculate the energy at the top is 1/2 mv squared, that's the speed of the thing at the top, plus the potential energy at the top. And then that energy at the top is going to all become energy at the bottom, and it's all going to be kinetic energy at the bottom. Since there's no potential energy at the bottom, we call that our 0 point. So the energy at the bottom is just 1/2 mv squared at the bottom. And then we just set these two things equal to each other. After you solve the first equation for the energy at the top, you get 2.5 mgr. You set that equal to 1/2 mv at the squared at the bottom, and you get velocity at the bottom when you're done solving for it is the square root of 5 times g times r. Again, it's only dependent on the gravitational constant and the radius of the loop. And this is the way it turns out through so many of these roller coaster equations. For the speed through anything, just about, you're going to find that it's only really related to very specific things that are usually just geometries of the track. How high is the track? What's the radius of the loop of the track? What's the radius of the turn on that track? What's the it's just heights and radiuses essentially when it comes down to it. Part C is to find the normal force on the passenger at the bottom, right? This is the passenger's perceived weight. In other words, this is the force that the car is pushing upward on the passenger with, the normal force at the bottom. So what we do here is we have a very similar equation to the one at the top. Oops, there we go. So here's the equation of at the top. And it's going to be very similar at the bottom, except for a couple of things. First of all, at the bottom of the track, n is not going to be 0. The car is definitely going to be pushing upward on your feet. And second of all, we're going to go ahead and put in our minus sign for mg to make sure we got that right. Because this is going to start to make it's going to start to be important. So all of our forces that are pointing upward at the bottom of the track are n and minus mg, but we also have, that has to be equal to the centripetal force because those are both pointing towards the center of our circle. So the centripetal force is mass times velocity squared over r, where velocity squared is the velocity at the bottom. Well, the velocity at the bottom is given by this formula right here, and we have all those numbers. We have the radius of the track, we have gravitational constant. We plug those things in and we solve for the normal force in this equation. And in the end, we get a normal force of n equals mg plus m times 5gr over r, and it turns out to be 6 times mass times gravity. In other words, 6 times your normal weight. So on these roller coasters, it's not that hard actually to get 4, 5, 6 times your weight in a turn, where you're pulling 4, 5, and 6 G's, they call that. Right? Generally, they don't like to go. Too much more than that, because if you go too much more than that for a very long time, you can start to lose blood in your brain and pass out. So right around 10 Gs, I think, let's see, is it 10 Gs? I think 10 Gs and more is where people start to kind of knock off when they're feeling those kinds of forces. Now, yesterday I did mention the idea of some forces that are kind of not real forces, but um, just the result of something getting in your way when you're turning. I like to use the analogy of driving in a Jeep without the doors, those Jeeps that people drive around in summertime don't have any doors on them. And you drive around in one of those things, and if you can imagine driving around in one that's got those really uncomfortable plasticky vinyl seats, and somebody's just like rubbed or just poured car oil, engine oil all over the seat or something, and you're wearing just your bathing suit. So you just got out of the pool, you're wet, and you're sitting on a seat that's super slippery and super oily, and you're not wearing your seatbelt, and your friend jerks the wheel to the left really hard, and you're going to go sliding right out of the car. And the reason you go sliding out of the car is not because there's a force pushing you out that way. It's because you were already going straight, and then the car turned, and there was nothing to hold you in the car. When you've got your seatbelt on, and there's a door on there, and there's friction between you and the seat, and everything else, there's a window, and you put your hands up on the dashboard if your friend turns really hard or whatever, you have all these forces that are going to stop you from flying out of the car, but it's not a force that makes you fly out of the car. The thing that makes you fly out of the car is just you keep going in that straight line direction when the car turns. It's just inertia, right? The fact that you feel like there's a force is just because you feel like you're not moving when you're in a car. It's a relativity thing. You feel like the world is moving around you, and so you think that when the car turns, your door is essentially, there's a force that's pushing you into the door, which is not true. The door is actually pushing on you. You're not getting pushed into the door. The door is pushing on you to push you back into the car and to keep you in that turning path that the car is experiencing. So the door actually exerts a centripetal force on you to turn you with the car. And the force that we think we feel inside the car is called the centrifugal force. So centripetal and centrifugal, different forces. Centripetal is actually a real force. The centrifugal force is what we call a fictitious force or a pseudo force that we kind of make up to just explain things in different frames of reference. Now, it's kind of ridiculous to consider that since everything that we do is in a different frame of reference. And so what might be a real force in one frame of reference would be considered a fictitious force in another frame of reference. And so it's kind of ridiculous to say that, but we do have to kind of make these standards so that we can communicate with each other, I guess. All right, that takes us to the end of 7.4 and those examples. Now we'll move on to 7.5. I think we have 7.6 as well to do. Yeah, we have 7.6. But these are kind of different laws. They're still circular motion. They're still center-based motion. But we're going to go on to a little grander scale here and talk about gravitation, universal gravitation. What does gravity behave like on a universal level, out there in the big picture? We have this historical story that we hear about when we talk about gravity, where Newton is sitting under an apple tree and an apple falls on his head, and all of a sudden he gets this incredible idea. Well, that may or may not be true. I doubt it, honestly. But Newton was certainly studying more than just things falling towards the earth. He was studying the movement of the planets in the solar system. He was studying how they attracted each other. How did the planets stay in these orbits? They were just, at this time, they were just starting to realize and just starting to kind of come out of the dark ages with the planets. It used to be astrologers way back in the day, even go back to Egyptian times and before that. These people that would study the stars, they thought that the planets were stars, and that they were special stars that somehow moved, that had thoughts and intelligence and moved through the heavens to predict events. And so they created this, these stupid stories and all this weird stuff, and we still use it today. That's the goofy thing. We still talk about I'm a Libra or I'm a Capricorn or whatever they are, when it's just ridiculous. They're planets that have a very regular motion. They don't wander through the stars like we thought they did. It's just that they're not stars. They're actually rotating around the sun just like we are, so it looks like they have kind of a random, funky motion. It's just a relativity thing. But at this time, Newton and other scientists, Copernicus and others, they had already figured out that we lived in a solar-centric universe, or what's often called a heliocentric, not a universe, but a heliocentric system, where the sun is at the center of it and everything else is rotating around that sun. And they're trying to figure out what is it that keeps them rotating around it. And they had discovered this idea of centripetal force. And Newton said, well, it's got to be some kind of centripetal force. We're going to call it gravity. And he worked out the math for it. And this is it right here. This is what is called the universal law of gravitation. All objects with mass obey this law as far as we know in the universe. We've never observed it to be different. If you take the mass of one object and multiply it by the mass of another object, and then you divide by the distance between their centers. So R is the distance between their centers squared. So mass 1 times mass 2 divided by the distance between their centers squared, you will get something that is proportional to the force that they feel. Excuse me. And the proportionality constant is this number, big G, which happens to be 6.673 times 10 to the minus 11. And the units that make it correct are meters cubed per kilogram second squared. The big G is called the constant of universal gravitation, and it is kind of one of the big mysteries out there. Why is it that masses draw each other towards themselves? I mean, why do they attract each other? And it even works with small masses, even though it's not a very big force with small masses. Excuse me. For example, if you take two lead balls about 6 inches in diameter, they weigh a lot, you know. A lead sphere 6 inches in diameter is a good 20 pounds or more. And you put them on a balance, which is called a torsion balance, and we can actually look at one of these. They're actually quite interesting. You put them on a torsion balance, which looks like, where's my Google? It's up here. Torsion balance. So what a torsion balance is designed to do is it's designed to allow things to attract each other. And there's this English guy named Cavendish who was the first one to do this experiment, and this is a similar whoa, that's not what I want to be. This is a torsion balance that is similar to his balance. Goodness, why can't I find this thing and look at it? Let me look at it. Okay. Anyway, this is what it looks like. So you have these two lead spheres on this torsion balance, and what this thing does, it allows these huge spheres to attract each other and to reach an equilibrium point where they're pulling on each other at a particular angle. And if you do this with these masses, and they're pretty heavy masses, it takes days for them to reach the balance point. It takes days for you to observe the attraction between them. In other words, the force between them, even though they're really close and they're pretty heavy, just takes forever. It's just a really, really tiny force. The acceleration is extremely small. However, the Earth is a huge sphere. It is so much bigger than we can imagine. Human beings just have a hard time imagining how big the Earth is. And then the sun is 1,000,000 times bigger than that. You know, it's just humongous. And so the gravitational force, even though their distance is pretty big between them, and so that R squared is going to get pretty big, the masses are so much bigger that there is a fairly strong attraction between the Earth and the sun. And there's even a fairly strong attraction between Pluto, the smallest planet, and the sun, because of the huge mass of the sun and the relatively huge mass of Pluto compared to what we're used to. So, and those people out there that say Pluto is not a planet, they're just wrong. They have no clue what they're talking about. They're worthless. But anyway, Pluto's always been a planet and always will be. So, the gravitational force dependent on the mass and the distance squared between them. It's what they call an inverse square law. So the farther apart things get, the smaller the force, the gravitational force between things get, and the bigger the masses get, the larger the forces get, the gravitational forces. Now, some people might think, well, that means that, you know, atoms that are so close together, they're going to have a huge gravitational field. Well, it turns out atoms are really close together, but they're so small in mass that it just doesn't work very well. And you'll have a chance to calculate and compare the gravitational field between atoms. It's just tiny. There is not any force going on there. It's different kinds of forces that act at the atomic level, much different forces. But the other implication of this is that gravity will not be the same at every point on Earth. Why? Well, because our distance from the center of the Earth is not always the same if you move around on the Earth. If you go up higher in altitude, you will actually lose gravitational force. You'll actually lose weight by going up higher, believe it or not. So let's take a look and see how much we're going to lose, how much weight we're going to lose. So over here we have an altitude chart for above the Earth. If you go to 1,000 kilometers, so 1,000 kilometers is 1,000,000 meters, then G becomes 7.33. It's like, you know, if you weigh 100 pounds, you lose 20 pounds right then and there, maybe 25 pounds. That's not bad, lose 25 pounds if you're 100 pounds just by going up 1,000,000 meters. The problem with that is the 1,000,000 meters is higher than the highest mountain on Earth by far. The highest mountain, I believe Mount Everest, is about 9,000 meters or something like that. So it's 1,000 times lower, or not quite 1,000, 100 times lower than 1,000,000 meters. But you can see that it gradually gets smaller and smaller gravitational pull as you get further and further from the Earth. However, you can lose some weight if you go up to Mount Everest. Mount Everest being at the 9,000 meters that it is, you're gonna lose approximately, if you're weigh 100 pounds, you're going to lose approximately 2 pounds of weight just from being higher. However, you're also going to lose weight just from being that high up because it kills your body to be that high up. And so you're gradually dying once you get above 22,000 feet anyway. Here they have an experiment. They have the schematic for Cavendish's experiment for measuring the gravitational constant G. Of course, Newton was able to get the gravitational G from doing his math, but Cavendish actually measured it by using this torsion balance that I was telling you about. And this diagram kind of shows how the balance works a little bit better. It's not obvious in the previous picture I showed you. But essentially what you have is you have these two huge masses, and then you have two smaller masses in between. And the smaller masses in between are on this torsion spring that allow them to rotate. And when they rotate into position so that they're right between these two bigger balls, that means that they've been attracted by the gravitational force of those bigger spheres. Okay, so now we're going to calculate the gravitational force on an object on a pool table, on a ball on a pool table. Is there much gravitational force on it, not including the gravitational force from the Earth? So we've got 3 balls, and we want to find out the gravitational force on 2, I guess, on ball 2. Or maybe we're doing it on all of them, I don't know. Looks like we're doing the gravitational force on all of them. I don't really know what we're doing, but we'll figure it out. So here we go. We want the magnitude of the force on mass 2 by mass 2 on mass 1. So mass 1 is feeling a gravitational force from the second ball, and it's going to be equal to G times M2 over M1 over the distance between them squared, and the G is just 6.67 times 10 to the minus 11. The mass of the balls is 0.3 kilograms, and the distance between them is 0.4 meters, so we square that and we do the math. Turns out that it's 3.75 times 10 to the minus 11 newtons, which is extremely tiny force. That is so tiny. 10 to the minus 11 newtons, holy mackerel. Then the force on mass 1 by ball 3. Same deal, except there's a different distance now. They're closer together. And so it's going to be a bigger force, 6.67 times 10 to the minus 11. It's twice as big almost, but still it's tiny, 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 right? Still quite tiny. Then we want to add those two forces together. One of these is a y force, one of them is an x force. So we add them together using Pythagorean theorem, square them first, add them together, take the square root, and then we find that the total net force magnitude is going to be 7.65 times 10 to the minus 11 newtons. So it's a little bigger than either of them, but not much. That's a tiny force. Those billiard balls will never feel that force. You want to know the angle of it, you take the y component over the x component, take the inverse tangent, you find the angle of that force. It's not going to help. It's not going to move them anyway. So, and then they do the same thing for a different set of, billiard balls. Now, another one is we have an astronaut standing on the surface of Ceres, the largest asteroid. He drops a rock from a height of 10 meters. It takes 8.06 seconds to hit the ground. And they want us to calculate the acceleration of gravity on Ceres. So we have a distance, we have an initial speed of 0, we have a time. We should be able to calculate an acceleration from that. And that's exactly what we're going to try to do. And then part B, we want to find the mass of Ceres, given that the radius is whatever it is, and then the gravitational acceleration 50 kilometers from the surface of Ceres. So we go ahead and look at our kinematic equations. It turns out we have a kinematic equation that involves the initial velocity, which in our case is 0, the time, and the acceleration, and the distance. And we have all those things except the acceleration. So we solve for acceleration and we get going. The acceleration, we're going to call it g on Ceres. That's what they do here. And then they plug in all the numbers, solve for g on Ceres, and you get 0.308 meters per second squared. So it's about 1/30th of the acceleration on Earth's gravity. It's pretty small. Then we want to find the mass of Ceres. Well, now that we know the gravitational acceleration of Ceres, we should be able to find other things that we need to know. For example, we should be able to find the mass. We should be able to find this g here is little g, and so we should be able to find the weight of something on Ceres. And then also we set that equal to the gravitational acceleration on Ceres, g times m, big M of Ceres times little m of our object divided by the distance, or by the radius of Ceres, which is the distance between them. And when we do that, we actually are able to find the mass of Ceres, solve for the mass of Ceres, because everything over here we know except for the mass of Ceres, which is 1.2 times 10 to the 21 kilograms. And then we calculate the acceleration of gravity at a height of 50 kilometers above the surface of Ceres. We use the same equation again, but we're setting the universal gravitational law equal to the weight law, and this g prime is going to end up being our g at 50 kilometers. In other words, the changed gravitational acceleration. When we solve for that, we get an answer that's slightly less, which makes sense. Now, in this particular problem, I want you to notice that we're setting weight equal to gravitational attraction. Well, isn't that true? The gravitational attraction force here that two objects feel is equal to the weight of an object on a planet if those two objects that are being attracted to each other are an object on a planet, right? On Earth, if you set mass times gravity, m times g equal to g times the mass of the object times the mass of the Earth over the radius of the Earth, and solve for little g on the left-hand side, you will get 9.8 meters per second squared. And that's where that actually comes from. That 9.8 meters per second squared can be derived from the universal gravitational law of Newton. Now, how does this work with gravitational potential energy? Turns out it's the same equation, except for two things. One thing is that you're going to have a negative sign on it. The other thing is that you're going to have a radius in the denominator, but not a radius squared, just a radius. So you can use this equation to calculate the potential energy of an object some distance away from another massive object. How close are we getting? I can feel it. We're almost there. So this is example 7.11. We have an asteroid with a mass 1 times 10 to the 9 kilograms, comes from deep space. Essentially, it's coming from infinity. And why do we care about that? Well, because what we're going to say is that the potential energy, the potential energy of this comet relative to some other object is going to be zero if it's so far away that, it just can't be measured, if it's at infinity. Why would it be zero? Because in the equation for potential energy we have G times mass over R, and if R is infinity, anything divided by infinity is zero. And so they want us to find the change in potential energy and the work done by the force of gravity of bringing this thing in closer to the sun. So, for example, to bring it into a point 4.0 times 10 to the 8 meters from the sun. Well, we just do a change in potential energy where our initial potential energy is going to be zero. It's going to be way out at infinity. Right? This R down here initially is going to be at infinity, so it's going to be whatever these numbers up here over infinity, it's going to be zero. And you'll see that down 2 lines, they actually do turn it into zero right there. But we still have this other term to deal with, gravitational constant times the mass of the Earth times the mass of the object, the asteroid in this case, divided by the radius between the asteroid and the center of the Earth. Remember, it's not the surface of the Earth. If you're talking about 50,000 feet of altitude, you're talking about your height above the surface of the Earth. But there's still more than that between the surface of the Earth and the center of the Earth. There's a lot more than that. 50,000 feet is nothing compared to the thickness of the Earth. So you have to take into account the distance from the center of the Earth. Then, once we've got this equation written down, which we do, we put in known quantities, we realize that the initial speed is going to be zero. Sorry, that the initial potential energy is going to be zero because it's out of infinity. And then we calculate everything, we get this number for delta PE, negative 9.97 times 10 to the 14 joules, I guess it is. And then the work that is done by gravity is just going to be negative the change in potential energy. So it's just negative PE. So that's instead of negative 9.97, it's 9.97 times 10 to the 14 joules. Now, why would they be the same? They would be the same because the gravitational field had to apply that gravitational force over that distance. And force times distance is work, right? And so what you've done is the Earth has done work pulling this asteroid in using its gravitational field, and the work has turned into potential energy for the asteroid. Find the speed of the asteroid when it reaches this distance, whatever it is, right? That's just conservation of energy, delta KE plus delta PE. So you have the PE on one side, the KE on the other side, in the end, you just solve for V, and you get 1.41 times 10 to the 5th, since you knew the delta PE was this negative 9.97 times 10 to the 14 joules. You just solve that in the end. Find the work needed to reduce the speed to half the kinetic energy at this point. Well, they just set it up in an equation where work is included as well now, and you're going to have a delta KE and a delta PE, except you're going to have half of the speed change, right? So it's going to go from 1/2. Let's see. They go from 1/2 mv. Oh, so we're going from 0 to 1/2 mv squared, where v is going to be half of what it was. 7.05 instead of 1.41 times 10 to the 3, it's 7.05 times 10 to the 2. And then you get negative 7.48 times 10 to the 14 joules. Turns out it takes just a little bit more energy to get it going a lot faster, twice as fast. Okay. We've overcome some kind of energy, hump in the energy road there. I love this question. Why is the sun hot? Because there's this great song from the 60s or the 50s. That was redone in the 90s. Oh no, I got a... Nice. Gotta turn off that thing, I guess. Anyway, there's this great song that was remade just probably in the 90s, I think, maybe the early 2000s, but I think it was the 90s, called "The Sun Is a Mass." No, it says it's called "Why Does the Sun Shine," and it's called. It starts off with "The sun is a mass of incandescent gas." That's the first line. So I love that song. It's a great science song. Just a guy and his guitar with his buddy that's playing an accordion. They Might Be Giants. It's a great group. All right, so we're kind of at the halfway point for this lecture. I think we're a little bit further. We have a thing that we call escape speed, which is the speed that you need to be going to launch something into space. And then we have section 7.6, Kepler's laws. So I'm going to come back in about 10 minutes and finish those off, and then take a look at some of the last homeworks. We'll be good to go. I want to take a break. I'll be right back.